Hi, I'm Mark Barsamian. In this video, we'll start a discussion of antiderivatives. This material is from the beginning of section 5.1. Just the first couple of pages, and example 1 is relevant to what we're doing in this video. The corresponding homework is this collection of just 2 problems in the MyLab system, but there is a large collection of exercises that is in the book that's not in MyLab. These are good exercises, and it would be a very good idea to do as many of those as possible. I'll be doing examples similar to some of these in the video today. We'll start with the definition of antiderivative. These words, capital F is an antiderivative of little f. It's important to notice the capital letter, capital F on the left, and the small letter on the right. That distinction I will maintain for a while. When talking about an antiderivative, I will use a capital letter. Well, what those words mean is the following. Little f is the derivative of capital F. That is, little f is capital F prime. It helps sometimes to think of this in terms of a diagram. To say that capital F is an antiderivative of little f means that if you start with capital F and you take its derivative, you end up with little f. So this sentence, capital F is an antiderivative of little f, just is another way of saying that little f is the derivative of capital F. So let's do an example. Is capital F equals x cubed over 3 an antiderivative of little f equals x squared? Well, the way that we answer that is we just check to see if it satisfies this condition. So we find capital F prime and see if it equals little f. Now, before finding the derivative of capital F, it will be useful to write it in power function form. In other words, we pull the constant out front. Capital F is the constant 1/3 times x cubed. Now we find the derivative. So our conclusion is yes, because capital F prime equals little f. So here we have a giant equation. On the far left, we have capital F prime. It equals this, which equals this, which equals this, which equals this, which equals this. So this giant equation is really just, in the end, saying that capital F prime does equal little f. Let's go on. Here's another question. Is this capital F an antiderivative of this little f? Well, let's check by finding capital F prime and seeing if it equals little f. And again, we'll start by rewriting capital F in a more helpful form. So we find that capital F prime equals this stuff, and that's not equal to little f. So our conclusion is no, capital F is not an antiderivative because capital F prime is not equal to little f. Notice that our derivative involved the chain rule. So if you made the mistake of finding the derivative incorrectly, if you didn't realize that you needed to use the chain rule, it's possible to reach the wrong conclusion in a problem like this. If you forgot about the chain rule and you just said that the derivative of this was equal to this without the 5, well, then you would have said, oh, it is an antiderivative. Capital F is an antiderivative. So the key in these antiderivative questions is to make sure that you find the derivatives correctly. Let's go on. Example 3. Is this capital F of x, x ln of x minus x, an antiderivative of this little f? Little f of x equals ln of x. Well, let's just find capital F prime and see if it equals little f. So we find our capital F prime, and we see that capital F prime is ln of x, which is little f. So we see that capital F prime does equal little f. Now the key thing here is to remember that we have to use the product rule to find a derivative like that. That's a product of functions. So when you use the product rule, you end up with that expression. And then also remember the rule for the derivative of ln of x. The derivative of ln of x is 1 over x. So a couple of old derivative rules have come back. Let's go on. In example 4, we're supposed to consider this capital F of x, e to the quantity x squared, and this little f of x, actually the same function, e to the quantity x squared. We're supposed to find out if capital F of x is an antiderivative of little f of x. Well, let's check by finding capital F prime. So to find the derivative of capital F, we have to use the chain rule because capital F is of the form of a nested function, an outer parentheses inner parentheses x. So we use the chain rule. The derivative of the inner function is easy. The derivative of x squared is just 2x. The outer function is an empty function, e to the parentheses. So its derivative is also e to the parentheses. So when I assemble all these parts from the chain rule details box, I get the following. I get e to the parentheses x squared times 2x. That's not the same as little f. So the answer is no, capital F is not an antiderivative because capital F prime is not equal to little f. Okay, well, let's try a different function for capital F. In question B, let's let capital F be this function. And we're going to see if that is an antiderivative of this function little f. So we'll check by finding capital F prime again. There are our chain rule details. When we assemble those parts, we find the following. Capital F prime is not equal to little f. So the conclusion is that capital F is not an antiderivative. Well, that's a bummer. We've had two different attempts. We've had two candidates of functions this one and this one, neither one of them were qualified to be called antiderivatives of this function, e to the x squared. Well, it turns out this is kind of a famous function. Here's some important facts from higher math. The good news is that this function, little f of x equals e to the x squared, does have an antiderivative. That's the good news. The bad news is that antiderivative cannot be written. This should say cannot be written in the usual way as a function made up of basic functions. That is, it cannot be expressed as a finite combination of simple functions. So that means that if you're ever presented with this question, is some function capital F of x that's written in an ordinary way, is that function an antiderivative of little f equals e to the x squared? The answer will always be no. But one must always justify that answer by finding capital F prime and confirming that capital F prime does not equal little f. Let's go on. The next example are a bunch of true-false questions. Question A. The constant function little f of x equals pi is an antiderivative of the constant function k of x equals 0. Now notice I've stopped using capital letters, but it will help to color code these things. That little f of x equals pi is the thing that is a candidate to possibly be an antiderivative, and this thing k of x equals 0 is the function that we're hoping that this green function might be an antiderivative of. All right, so how do we find out whether this sentence is true or false? Well, what this sentence would mean, if it's true, would be that little f prime equals little k. So we should investigate this by finding little f prime and seeing if it equals little k. So when we find little f prime, we find the derivative of pi. Well, pi is a constant function, so its derivative is 0, and that equals our k of x. So the conclusion is yes, that function is an antiderivative, and so this sentence is true. Little f is an antiderivative of little k. That's a true sentence. Question B. The constant function k of x equals 0 is an antiderivative of the constant function f of x equals pi. Well, so those are the same two functions we were dealing with before, k of x equals 0 and f of x equals pi, but they're playing different roles now. The k of x is the thing on the left that we're investigating to see if it's an antiderivative, and the f of x equals pi is the thing on the right. So we have to figure out if this sentence is true or false. Well, let's find k prime and see if it equals little f. Well, when I find k prime, I get the number 0, and that's not what little f of x is. So not an antiderivative. So this sentence is false. If I say that k of x equals 0 is an antiderivative of the constant function f of x equals pi, I've lied. That sentence is not true. What about question C? The constant function k of x equals 0 is an antiderivative of itself. Well, that's true, but we should explain why it's true. So there's our explanation. Little k prime equals little k. So little k is an antiderivative of itself. How about question D? The function g of x is an antiderivative of itself. Well, that seems clearly true as well. So let's just go ahead and circle true, and let's show why. When I find g prime of x, I find that g prime of x equals g of x. So g of x is an antiderivative of itself. So this is true. Now, what about question E? Is 5e to the pi an antiderivative of itself? Well, you're supposed to be duped and make a mistake here. Notice we found that the function 5e to the x is an antiderivative of 5e to the x. So you're supposed to be duped and think, oh, well then 5e to the pi is going to be an antiderivative of itself as well. But the thing is, whether or not it is an antiderivative, you're going to have to show why. And that is going to involve finding h prime. So let's just find h prime and see what it equals. So h prime is 0. The derivative of 5e to the x is 5e to the x, but the derivative of 5e to the pi is the number 0, because 5e to the pi is a constant function. So the answer to this question is false. To say that h of x equals 5e to the pi is an antiderivative of itself is false. Let's go on. Question 6. For which values of n is this thing, capital F of x equals x raised to the n plus 1 power divided by n plus 1, for which values of n is that an antiderivative of this function, little f of x equals x to the n? Well, let's investigate by finding capital F prime. Well, we start by rewriting capital F of x. We need to find capital F prime, but capital F is not given to us in a form that's the best for finding its derivative. We put it in power function form. That's important because that function capital F is presented to us looking like a quotient. So we might be duped into thinking we need to use the quotient rule, but we don't. We should write it in power function form and then find its derivative. So when we find capital F prime, first of all, since we put capital F in power function form up here, the derivative is quite a bit easier than it would be if we used the quotient rule. The first step is we use the constant multiple rule to pull this constant multiple out front. That leaves us with this derivative to do, the derivative of a power function. We use the power rule and we get that as the result. Notice we have some nice cancellation. These factors cancel. And then we're left with just x to the n, which is little f of x. So it looks like capital F is an antiderivative of little f. But wait a second, look at our question. Our question says, for which values of n is capital F an antiderivative of little f? What's up with that? I mean, it seems like it always works out. It seems like capital F is always an antiderivative of little f because capital F prime is always equal to little f. But let's go way back to the beginning of this question. Look at that expression for capital F of x. For which values of n does that expression even exist? If n is equal to 5, capital F would be x to the 6th over 6. If n was equal to 0, that would be, capital F would be x to the 1 over 1. If n was equal to negative 5, capital F would be x to the negative 4 over negative 4. So it seems like when x is a real number, then you get a function, capital F of x, that is described by this expression. But wait a second. What if n were the number negative 1? When n equals negative 1, capital F does not even exist. So capital F could not be an antiderivative of little f in that situation because capital F doesn't even exist. We realize that that's the only time when capital F of x does not exist. When n equals -1, capital F does not exist. So capital F is not an antiderivative of little f in that case. So the answer to the question, for which values of n is capital F an antiderivative of little f, we realize the answer to that question is for all real numbers n except n equals -1. So for all of the other values of n, for all real numbers n that are not equal to -1, then this equation, this big long sequence of equations, tells us that capital F of x will be an antiderivative of little f. But the original question was this one, for which values of n? And we realize that it's for all real numbers n that are not equal to -1. Capital F of x will be an antiderivative of little f. That's the end of that example, and that's the end of the video. Thank you.